Okay, so continuing our discussion of genome assembly problem, today we are going to look at the greedy algorithm for genome assembly in more details. So in the last lecture, I gave you the overview of how greedy algorithm works. The focus of this lecture will be to analyze the greedy algorithm in significantly more details. So let's get started. So let's recollect the basics from last couple of lectures. So remember that in the genome assembly problem, you are given a set of reads and we are trying to reconstruct back the original genome sequence from where these reads were sampled from. So we looked at one of the first problems for solving genome assembly problem, that is the shortest common superstring problem. Here as input you are given as a set of strings, for example a set of reads, and we denoted this as set F, and as output we said that we will follow the principle of parsimony, that is we will look for the shortest possible string such that every string is a substring of that superstring. So in other words, we are looking for the shortest possible string S such that for every input string F is a substring of S. We considered this example below, and for this example S is the shortest common superstring. When we studied this problem in more details, we realized that the shortest common superstring problem can be framed as a standard graph theoretic problem, which is the maximum weight Hamiltonian path. This was an interesting connection to see between the string problem and a graph problem. And subsequently we also said that the shortest common superstring problem has been proven to be NP complete, and which also means that the efficient exact algorithms for solving these problems are unlikely that will scale to large inputs, because NP complete problems are intractable. So subsequently we said that okay, when you have an NP complete problem, then we can look at approximation algorithms or greedy or heuristic algorithms, and for that we looked at a greedy heuristic algorithm, which is actually very conceptually simple and efficient. So in the greedy algorithm, the basic concept is that at every step of the algorithm we are making a greedy decision based on the suffix prefix overlaps between the strings. So the greedy algorithm worked as following. You have a collection of strings, capital F, right. So we created a graph where you have a vertex for every string, and so you have a vertex with label small f. Initially the graph has 0 directed edges, and as the greedy algorithm proceeds we will look for pair of strings which have maximum suffix prefix overlaps, right. So we will look for those pair of strings such that the first string has no outgoing edge and the second string should have no incoming edge, and among those pairs we will look for the maximum suffix prefix overlap and connect the edge between them. So if let us say F1 comma F2 is such pair of strings which has maximum suffix prefix overlap, then we will connect a directed edge from F1 to F2, and we will repeat this step 2 until we have a connected component, that is until we have a single connected component which forms a chain in the graph. Once you have connected all the strings with each other, finally we return the string spelled by the chain. So we looked at the following example to illustrate this algorithm. Here you have 5 input strings, right, and as I said, the greedy algorithm works by looking for maximum suffix prefix overlap length. So in this case it finds a suffix prefix overlap length of 2, and therefore it connects these 2 vertices. It will continue this process until you have a single connected component at this point, and when you have a single connected component it will always be in the form of a chain, because you are always looking for those pair of vertices in which the first vertex has no outgoing edge and the second vertex has no incoming edge. So, you are always connecting such vertices, and as a result the end output graph will be a chain. And finally, what we can do is we can output the string by joining those conjugative strings. So, for example, I would join these two strings, and by joining I mean that I would merge the overlapping suffix prefix. So, in this case I would spell the string AAA, and I would not spell the prefix which is already there in the previous string. So, in that case it would be AAAB, and then in this case AB is a prefix which is already existing. So, I will not consider that. I would consider character B here, and then character A here. So, the final string output of the greedy algorithm is AAA BBBA. Now, greedy algorithm, as you can see here, is guaranteed to output a common superstring, that is, each of these strings is a substring of my output. So, for example, you can see that AAA is a substring, right? AAB is also a substring, ABB is also a substring, and so on. So, in this case we are guaranteed to output a superstring, except that greedy algorithm is not guaranteed to return the shortest superstring, right. So, we are not solving the shortest common superstring problem exactly. We are identifying a superstring using this greedy algorithm, and this superstring is not guaranteed to be the shortest string that satisfies this property. So, in that case right now it is a heuristic, right. So, let us proceed further, and I hope by now how this greedy algorithm works is clear to you. And as you can see, this is conceptually very simple. At every point we are making a greedy decision based on the maximum suffix prefix overlap length between a pair of strings. So, now for this lecture, the goal of this lecture is to analyze the greedy algorithm in more details. That is, we will first analyze the runtime of the greedy algorithm. Second, we will look at how much longer can the output of greedy algorithm be compared to the shortest superstring. That is, are there any worst case guarantees, that is, the greedy algorithm cannot output significantly longer strings than the shortest superstring. So, we will see what guarantees exist for greedy algorithm. And finally, the third question is a more practical question, that is, if we use greedy algorithm on a collection of sequencing reads, and suppose we run the greedy algorithm and get the output string, then should a biologist trust the output? That is, whatever output we see, does that correspond to the true genome sequence, and should the biologist trust the output? So, we are going to address these questions one by one in the next slides. So, as the first step, let us analyze the runtime of greedy algorithm. And to run this algorithm more efficiently, well, what we can do is, suppose we have a set of strings f, we can, let us say, we use this notation to denote the count of strings in f, and use this double vertical symbol to denote the sum of length of all the strings, right. So, in this case, for example, on the example shown on the right, capital, so the number of strings is 5, and the total sum length in this case is 3 times 5, that is 15. So, these are the notations that we are using here. Now, to run the greedy algorithm efficiently, what we can do is we can pre-compute all versus all longest suffix prefix overlap lengths, because at every step of the greedy algorithm we have to look for the longest suffix prefix match. So, what makes more sense is we can pre-compute overlap lengths between all pairs of strings, right. So, I am showing this illustration on the right hand side, where I can assume you can build a complete graph. You can compute all f times f minus 1 overlap lengths, so that you have the information that you need while running the greedy algorithm, right. And remember that this problem we have already studied before in module 2. So, if you remember the generalized suffix trees and the problem of all pairs suffix prefix problem, then you would remember that this problem should sound familiar to you. That is, we can compute all versus all suffix prefix overlaps using suffix trees very efficiently. So, using suffix trees, we know that all suffix prefix overlaps between all pairs of strings can be computed in this much time. That is, the total length of the strings plus the number of strings square, and this comes because we have to report the output. So, this is also the output size, right, because the output size. So, this is the output, because as output you are outputting this overlap lengths between all pairs of strings. So, your output length will be an array of integers of size f square. Now, this we already know from module 2 on how to do this step, and if you do not remember, then you can go back to the earlier lecture if you want to revise that. So, now once you have access to the suffix prefix overlap lengths, what we need to do is simply sort these overlap lengths, right, and we can add the directed edges based on the overlap lengths and spell the output sequence, right. So, remember that one detail I have missed here is that we have to also keep track of the degree of the vertices, so that we can keep some Boolean array to remember that, right. And once we do that, we can add the directed edges. That is, because the greedy algorithm favors longer suffix prefix overlap lengths over the shorter overlap lengths. So, we can sort all these overlaps in non-increasing order and continue to build this graph until we form a single connected component, right. So, we can use the overlaps based on their overlap lengths, and we can spell the final output sequence to give the greedy output. Right. So, based on this, the runtime of this algorithm will be the total sum length of the strings plus the time to sort all the integers. So, because we have to sort all these integers in non-increasing order, so that we consider the higher overlap lengths first. So, this is the sorting step, and the combined complexity is basically given by this step, because this is a slower step than compared to computing suffix prefix overlap lengths, and this gives you an efficient algorithm which is actually conceptually simple, and you have a polytime complexity to solve the greedy algorithm. So, this completes the runtime complexity analysis, right. So, we have understood how much time greedy algorithm takes on a collection of strings. So, let us proceed forward and move to the second question for this lecture, that is, how much longer can the output of greedy algorithm be compared to the shortest superstring. As I mentioned earlier, that the greedy algorithm guarantees that the output is a superstring, but it is not guaranteed to be shortest superstring. So, how long can the superstring output be compared to the shortest superstring? Let us look at that. So, in computer science literature, we have several approximation results for the greedy algorithm. It has been proven that the output of greedy algorithm is at most constant times the length of the shortest common superstring. So, for example, if greedy algorithm is outputting string S prime and the shortest common superstring is S, then we know that the length of S prime is less than equal to a constant times S. And this constant has been proven to be 4 initially by a paper in 1991. Then subsequently a tighter bound came for this value C. It was proven that this value C can be further tightened to 3.5, and more recently a further reduction has been obtained on this constant factor to 3.425. So, these are theoretical works which have mathematically proven this inequality and proven that what are the C values for which this inequality can be proved. So, the best, based on these results, the best factor for C available to us is right now 3.425. Now, let us look at a bad example for greedy, right. So, what is a hard example for greedy algorithm where the output of greedy algorithm is significantly longer than the shortest common superstring? So, let us consider such an example. So, as a notation, let me denote a character raised to power integer. So, for example, a raised to power 3 indicates character A repeated 3 times. Similarly, a raised to power 5 indicates character A repeated 5 times. So, with that notation in mind, let us consider this example where you have 3 input strings, that is A, B raised to power k. Your second string is B raised to power k C, and your third string is B raised to power k plus 1. Now, in this case, what can greedy algorithm do? That is, what would be the output of greedy algorithm? So, you have 3 strings, and as you know, the greedy algorithm favors the longest suffix prefix overlaps first. So, maybe it will see that there is an overlap of length k between these 2 strings. So, maybe it will connect these 2 strings first, and then there is no choice, that is the only pair of strings left to be connected is these 2. So, you will naturally connect these 2 vertices to form a path. Now, observe that in this case the output of greedy algorithm will be the string spelled by this path, that is A B raised to power k, then C, and then B raised to power k plus 1. However, for this particular example, the shortest common superstring is A B raised to power k plus 1 C. That is, if you can verify that. So, if you can verify that the first string is a superstring of this, the second string is also a superstring of this, and the third string is also a superstring of this, and this is shorter than the output of greedy algorithm. And if you actually check the ratio, so for example, the length of greedy output is in this case 2k plus 1, 2, 3. So, it is 2k plus 3, whereas the shortest common superstring is k plus 3. Now, you can already see that for very large values of k, the greedy algorithm output is 2 times longer than the output of shortest common superstring. So, that is, if we were talking about this constant factor, you already see a constant factor of 2 here for very large values of k, right. So, in other words, the length of the greedy output is 2 times the length of shortest superstring in this case. And this is a hard example for greedy algorithm, that is, it is outputting a significantly longer superstring compared to the shortest possible superstring. So, based on this example and given these results, observe that none of these results prove that the constant factor is 2. The proven results are constant factors greater than 2. So, based on this example, it has been conjectured that the greedy algorithm has an approximation factor of 2. That is, there is a hypothesis that it may be possible to further prove that the inequality holds for a factor of 2. However, this is yet to be proved or disproved. That is, maybe there is another worst case example where a factor of more than 2 exists, or we just need a better proof technique to prove that the constant factor, that is the approximation factor of 2, exists for the greedy algorithm. Now, here I am not discussing the proofs themselves, I referred you to the papers for these. So, these are the papers where the proofs have been given, and these are significant. So, these are out of the scope of this syllabus because the proof techniques are very advanced. If you are interested, please go and check these papers. So, this is an open problem in theoretical computer science, that is to prove an approximation factor of 2 for greedy algorithm. Now, so this confirms that the output of greedy algorithm cannot be significantly longer than the shortest superstring. That is, the output of greedy algorithm is within a constant times factor of the shortest superstring output. Now, let us move to the third and final question for this lecture, that is, can we use greedy algorithm on a collection of sequencing reads in practice? That is, whatever output that the greedy algorithm is producing, can we hand over that output to a biologist and ask them to trust the output? So, let us look at an example to answer this question. Suppose my hypothetical unknown genome sequence is a long time. So, this is a hypothetical genome sequence. Here I am using an English text, but obviously in reality it would be, the genome sequence would be in terms of A, G, C and T's. But for an example, let us consider a hypothetical case where the genome sequence is a long time and you have these underscore symbols in between. Now, suppose I have input reads of length 6. So, my first input read is ng_lon, my second input read is _long_ and so on. So, in this case you have 10 input reads, and using these input reads we can again run the greedy algorithm and see what would the greedy algorithm output. Now, you have already seen how greedy algorithm works. So, I encourage you to try this yourself. You can build a graph with 10 vertices and connect those pair of vertices as we have described in the greedy algorithm. Now, I encourage you to try this yourself, and once you finish the analysis, you will find that the greedy output is a long time. That is, if you observe that this is a valid superstring, right. So, this is a valid superstring because if you check each read is a substring of your greedy output. So, for example, if I look at ng time is a substring of your greedy output, and similarly all these reads are substrings of your greedy output. But what has gone wrong? Well, observe that the output does not match the original genome sequence, and this is a problem because now if you think of giving the greedy output to a biologist and ask them to trust your output, then they will not be happy because they may say that look, your genome sequence looks much shorter than what I expected. So maybe they have some expectation of that the genome length is x and your genome length is significantly less than x, then maybe they will report back that your output is incorrect. So in general, what we are finding here is that the greedy output is not guaranteed to match the target genome sequence. And why is that? Well, unfortunately what happens is that the repeats are collapsed in practice, and this is a known weakness of the greedy and shortest superstring ideas. Because if you think about it, in the shortest superstring formulation, what we are looking for is a shortest string that is compatible with all the reads. And because we are looking for this is based on a parsimony principle in which we are looking for a shortest superstring, that automatically results in collapsing of repeats. That is, if you have many repeat copies, the copies in your output may be fewer than the true sequence. So here you have only 2 copies of the repeat, whereas the actual genome sequence had 3 copies of this repeat. This is a known weakness of the greedy algorithm. And you can also think about another question, like what if you had longer reads? So for example, in this case I am considering reads of length 6, but what if I have another example in which reads have length 8 instead of 6? So if you have, let us say, longer reads that cover the genome, then what would happen? And intuitively you can think that maybe once you have longer reads, maybe then greedy algorithm will start working correctly, right. So again I encourage you to try this yourself. So what if you can, now you can build another read set where your reads are of length 8 and then solve the greedy algorithm, and then maybe you will find that the greedy output is correct and you will recover the exact number of repeat copies in your output. So let us formalize this idea better. It turns out that under certain assumptions, greedy algorithm is guaranteed to reconstruct the genome. So we can make a few assumptions, like for example, reads have no sequencing errors. So whatever reads we are giving as input, they have no sequencing errors. So each read is guaranteed to be a substring of the genome. We will also assume that reads are substring free, that is, we have defined this substring free property in the last lecture. We will assume that there is sufficient coverage, that is, reads cover the entire genome, because if reads do not cover some part of the genome, then there is no hope of reconstructing the genome sequence. And finally, one property that is specifically required for greedy algorithm is that we want every repeat of the genome to be bridged. Now I have not formally defined what this term bridged means. Let me do that in the next slide. Under these assumptions, what we will prove that the greedy algorithm is guaranteed to reconstruct the original genome sequence. So for proving that, let me give you some notations. Let me denote S subscript T superscript L as the length L substring of genome G starting at position T. So let us say this is position T and this is a substring of length L starting at position T, and I am noting this as S T L. So this is a simple notation to denote a substring of the genome sequence G. Now let us define repeats in a genome. So a pair ST1L and ST2L. So you have a pair. This is a repeat in the genome if both of these substrings are equal and T1 not equals T2. that is these substrings occur at 2 different positions in the genome and these substrings are equal to each other. So, then you have a repeat in the genome, right. So, this is a simple definition. Moving on, we say that a substring STL in the genome is bridged if and only if there exists at least one read which covers this substring and at least one character on both sides of the substring. So, for example, if you see the figure below, you have a read which bridges this substring because it covers the substring as well as at least one character on left and at least one character on right. And in this case we say that the read bridges this substring. Finally, we can say that a repeat is bridged if at least one copy of the repeat is bridged. So, if you have a genome where you have a repetitive substring, so you have substring starting at T1 and another substring starting at T2 and let us say these 2 substrings are identical, then this repeat is said to be bridged if at least one of these copies is bridged. So, if one read is bridging the second copy, let us say, then we can say that this repeat is bridged. So, only one of the copies has to be bridged, right. We do not require both copies to be bridged. So, if at least one copy of the repeat is bridged, then we say that the repeat is bridged. Okay. So, now with these definitions I can put forward the following claim. Given a genome sequence G and a set of reads, the greedy algorithm is guaranteed to reconstruct the original genome sequence G if every repeat in the genome is bridged. And for this we are going to give a proof which will work by contradiction. Let us say that the greedy algorithm makes its first mistake when it connects read Ri to read Rj, because remember that in the greedy algorithm we have different vertices for all the reads and let us say initially it worked correctly, the greedy algorithm made the correct decisions, but the first incorrect decision that the greedy algorithm made is when it connected Ri to Rj, right. So, let us say that is the first incorrect decision that the greedy algorithm made. So, it connected read Ri to Rj with overlap length L, that is the maximum suffix prefix overlap length between Ri and Rj is L. Now, we can analyze 2 cases, like why would this be a mistake? Well, this can be a mistake because of 2 reasons. It may be that Rj is actually the successor of Ri in genome sequence G, but the mistake is due to incorrectly computing the suffix prefix overlap length, because in greedy we are always picking the maximum suffix prefix overlap length. So, for example, if you have strings A B B and the second string is B B B, then the greedy algorithm will always pick the maximum suffix prefix overlap length. But otherwise in reality it may happen that the overlap length should have been 1. So, that is the first case where the greedy algorithm can make a mistake. The second case is where Rj, the read Rj is not actually the successor of Ri in G, that is Rj is somewhere should have far apart and Ri is sampled from a far away region in sequence G. We will prove that in both cases we will arrive at some contradiction, and because of those contradictions we will be able to prove that the greedy algorithm is actually guaranteed to return the correct genome sequence. Let us analyze these 2 cases one by one. So, in case 1, Rj is actually the correct successor of Ri, but we made a mistake in judging the overlap length between Ri and Rj. That is, the greedy algorithm considered the overlap length to be L, whereas the correct overlap length was shorter. Now, in this case, observe that because of this overlap length, we know that these, that is, we know that a suffix of length L of read Ri matches a prefix of length L of read Rj, which also means that there is a repeat in the genome. So, because of this overlap, what we can infer is that there is a repeat in the genome sequence of length L. But observe that now no read exists to bridge this repeat, which leads to a contradiction, right, because Rj is the successor of Ri, and if there is a read which exists to bridge this repeat, then Rj will not be the successor of Ri in genome sequence G. So, that means that there is no read to bridge this repeat, and for this case we have arrived at a contradiction, because our assumption in the claim is that every repeat is bridged. So, in this case 1 we have already arrived at a contradiction. Let us move to case 2, where in the actual genome sequence G, read Rj is not a successor of read Ri, that is, they occur at different locations in the genome sequence G. Now, in this case again observe that we have repeats in the genome, because you have a repeat of length L that are equal. So, these, because of the suffix prefix match, we know that there is a repeat in the genome sequence G. Now, because of this repeat and because we know that every repeat in the genome is bridged, let us say that this repeat is bridged by some read Rk. So, let us say that the first repeat copy is bridged by read Rk, but if that is the case, then in the greedy algorithm we should have prioritized the overlap between Ri and Rk first, because observe that if Rk bridges this repeat, then the overlap length between Ri and Rk is greater than L. So, the overlap between Ri and Rl is greater than L, and as a result, because in the greedy algorithm we are always favoring longer overlaps first, it means that the greedy algorithm should have prioritized the overlap between Ri and Rk or some other read with higher overlap, that is, Ri should have an overlap with some other read. Greedy algorithm should not have picked Rj, and because of this argument we again see some contradiction, that is, why would greedy algorithm pick Ri and Rj first, and as a result we arrive at a contradiction for case 2 as well. And this completes the proof, that is, for both cases we have proved that we have arrived at a contradiction, proving that the greedy algorithm is guaranteed to reconstruct the original genome sequence, assuming every repeat in the genome sequence is bridged by some read. Now, if you look at the example where the greedy algorithm failed to reconstruct the genome, then observe that there is a repeat long and here there is a repeat long, right. So, these are repeats. So, these are two repeats in the genome sequence and there is no read which is bridging this repeat copy, and as a result, for this particular example the greedy algorithm is not guaranteed to reconstruct the original genome sequence. So, this completes the analysis of greedy algorithm, and what we have seen is runtime of the greedy algorithm, we have seen the approximation factors of greedy algorithm, and we have seen under what conditions can a biologist trust the output of greedy algorithm. That is, under some conditions the greedy algorithm is guaranteed to reconstruct the original genome sequence. So, this completes the analysis of greedy algorithm, and in the next lecture we will look at different algorithms for solving the genome assembly problem. Thank you.